Okay, welcome back to our latest unboxing video. This time we got a sweet test. We got the Math 265 Fall 2017 final exam. It's going to be awesome. I've heard some good things about this. Let's go ahead, let's open it up, and let's see what we got. Okay, what do we have here? Ah, what a nice looking test it is. Right away I see that this test has some really beautiful features to it. Notice that the paper here is actually not white, it's gray. If you see, here's a piece of white paper, you can definitely see now how gray it is. Now, there's about 10 different colors, and among those 10 colors, we can definitely say that gray is one of them. And so it's a very popular color. What are some other things that we can see? Well, no question on the front page. They want to give us some time to sit and to panic. Hate it when they do that, but it probably makes it more fair. We get our place to put our name up here in the corner. Looks like it's going to be a 7-problem test. It's a little bit short for test, but you know, that's okay. Trade-offs, we'll take it. Some other notes. This test is going to have boxes where they write the scores. I guess we won't write in those. Anything that we should see? Well, you know, it's always good to read the instructions on these tests. It says the exam here, closed book, closed notes, and no calculator. Now, the no calculator thing is kind of a more modern take. If you look back at other tests, you'll see that they allowed calculators. But nowadays, they want to go more one-on-one, you against the test. So there's a trade-off here. I like the way that this direction is going. We'll have to see what happens. But one of the things this means is definitely computations can't be that bad. Let's see, we'll answer each question. Don't need to simplify unless otherwise indicated. That's good. Show your work legibly. Well, okay, that might be a test for some of us. But all right. And if we don't show our work, well, we may not get credit. Okay. Well, you know what they say, you got to really get into the test if you want to know what it's like. So let's go ahead and dig into it. We're going to take this test apart. So I'm going to start by turning it over. And we're going to remove the staple here and see what we got. And here we go. All right. Good. Now, as I was doing this, let me just pause here and notice that the back page is blank. In fact, so is the other side. It's a blank page on the back. This is not a printing mistake. This is actually done intentionally. We want to give people a blank page. That's a nice for them to do that. Okay. So normally, people would take a test. They'd skim through it first. But let's just go ahead. Let's go through it one by one. Let's see what we got. Let's see what we got here. All right, so let's begin. Turning it over to problem 1. Yeah. Now, what does it say? Well, let D be the solid. Okay, this is a solid problem. And it tells us 0 less than or equal to y less than or equal to x, 1 less than or equal to x squared plus y squared less than or equal to 9, and 0 less than or equal to z less than or equal to arctangent of y over x. Now, I just got to say there, as soon as I see that arctangent on that test, this has got to be one of those Butler tests. Butler is addicted to arctangent, so you got to watch out. Okay, what else do we have? Oh, it says here arctangent of y over x has a simple expression in cylindrical coordinates. Okay, so we're going cylindrical on this one. Now, as a reminder, if we're doing cylindrical, we probably want to recall dv is r dz dr d theta, so we'll probably need that at some point. And it says here, given D has a density function, density at xyz equals 3z, find the total mass of the solid D. Okay, now we see they provided a picture here. That's nice of them. Now this, I will say, is a little bit of a confusing picture because it almost looks like this is one continuous line here. But in fact, if you look closely, you'll see this is one piece. There's a slight curve here. And this is another piece, and it's this straight line segment here. It's a little bit clearer to see what's happening here on the back. Now, one of the things is the arctangent. We don't like arctangent. We want to get rid of it. Now, how do we do that? Well, let's think about it. It tells us has a simple expression in cylindrical coordinates. So let's see if that's true. So let's start. Arctangent y over x. Well, what can I do with that? Well, I can say that since I'm in cylindrical coordinates, y is r sine theta and x is r cosine theta. The r's will cancel. Sine over cosine becomes tangent, so this is arctangent of tangent theta. But wait a second, arctangent is just a funny way of saying inverse tangent. So if we have arctangent of tangent theta, that means we've got to have ourselves a theta. That is beautiful. Okay. Now let's think about what's happening here in the plane. So the plane, we look at those two pieces. We know 0 less than or equal to y, less than or equal to x. So I'm below the line y equals x. And I'm in between two circles, radius 1 and radius 3. Remember 9, that should be 3 squared. So I got a radius 1, and I got a radius 3, and that means our region looks a little bit like that. Now y equals x, also known as theta equals pi fourths. Okay, so we can describe our region now really simple. We can say that 0 is less than or equal to theta, less than or equal to pi fourths. Then we can say that 1 less than or equal to r, less than or equal to 3. And of course, here, for z, 0 less than or equal to z, less than or equal to theta. All right, beautiful region, beautiful region. And okay, what do we do now? Well, let's set it up. We know mass is going to be the integral over our solid of density. Okay, good. Well, that's the integral. Density is 3z. Now, nice thing for us, 3z already in cylindrical coordinates. We don't have to do anything. So that says as 3z. We already noted it since it's cylindrical. dv, that's going to be r dz, dr, d theta. And we already found our bounds. 0 to pi over 4. Then we have r, 1 to 3. And then we have z, 0 to theta. Okay, good. Well, we're most of the way done with this problem. Okay, let's go ahead. Let's finish this up. Let's see what we got. Integrate with respect to z. There's a z there. So this will become integral 0 to pi fourths, integral 1 to 3 of 3 halves z squared r, evaluated z equals 0 to z equals theta, dr d theta. Well, this becomes 0 to pi fourths, 1 to 3 of 3 halves of theta squared r, dr d theta. Now here you'll notice that these bounds are both numbers, which means that we can do our classic trick, pull things apart into two integrals. So let's go ahead and do that. If we do that, we're going to get the integral 0 to pi over 4. I'll go ahead and put the 3 in there. 3 theta squared d theta. And then we're going to have the integral 1 to 3 of 1/2 r dr. Well, the 1/2 doesn't really make sense there, but go ahead and throw it in there anyways. And what do we get? Well, this is going to be theta cubed from 0 to pi fourths. And here, this will be 1/4 r squared from 1 to 3. And if we do this, now here, on this side, r squared, we're going to get 1/4 times 9 minus 1, which gives us 2. Here we're going to get pi cubed over 4 cubed, which is 64. And therefore, we get our final answer is pi cubed over 32. Nice! Nice clean answer. Nice way to start off the test. Good warm-up. Okay, moving on. Let's look at problem number 2 as we go through this test. Okay, problem number 2. Directional derivative. Now these are great problems. I love directional derivatives because they're really simple. So whenever I know it's a directional derivative problem, in this one, it's really easy to tell it's a directional derivative problem because they told us. Yeah! Okay, so what do we do? Well, that means that what? Well, we're going to take the gradient of something, in our case g, evaluate at some point p dot u. So every directional derivative you do in this way. Gradient dot u. U is a unit vector. So this is the key. U is the unit vector, and that's the direction. Okay. So we have our function. Let's take a look. It's a 3-variable function. Perfectly fine. So we're going to start by taking the gradient really quickly. So the gradient of our function, gradient g of x, y, z. Okay, what do we do? Well, it's going to be a vector. Take derivative with respect to x first. 6xz minus 1, and that part doesn't contribute anything, comma. No y, no y. And then I'm going to get 1 over 1 plus y squared times the derivative of 1 plus y squared, which is 2y. And that's that. And then 3x squared. That's it. That's it. So there's my gradient. I need to evaluate that at my point. So gradient g at 1, 1, 1, what would that be? Well, plug in 1, 1, 1. 6 minus 1, 5. Here I have 1 over 1 plus 1, so that's a half, times 2, which is 1, then 3. 5, 1, 3. Good. Halfway there. We need the u. Well, what is the u? Well, we're at the point 1, 1, 1. We want to go to a different point, 7, negative 1, 10. So here's 1, 1, 1, and over here is 7, negative 1, 10. Probably not, but let's just pretend. So I'm going in that direction. Well, okay, so first step is to say that the vector between these 2 points is the differences. So that would be 7 minus 1, 6, minus 1, minus 1, negative 2, and 10 minus 1 would be 9. So 6, negative 2, 9. Obviously not unit vector, so let's figure out what that magnitude is. So if I take the magnitude of 6, negative 2, 9, that would be the square root of 36 plus 4 plus 81, square root of 121, and lo and behold, they gave us a nice answer. That is 11. Okay, so we're almost done. That means our unit vector, u, will be 1/11 times 6, negative 2, 9. Okay, so we've got our u, we've got our gradient, now we need to take the dot. So we have our answer will be, let's go ahead and rewrite. Gradient of g at 1, 1, 1 dot u is going to be 5, 1, 3 dot 1/11, 6, negative 2, 9. Okay, now, what do we have? Well, the 1/11th, just put that downstairs. 5 times 6 is 30. 1 times minus 2, minus 2. 3 times 9 is 27. Now, if we didn't have to simplify any further, we could stop here, but notice this one is a simplify. Now, usually when you see a simplify as much as possible, that means it simplifies a lot. Let's see if that's the case here. Well, 27 minus 2 is 25. Toss on another 30, that gives us 55 over 11. But that's pretty easy to see that the bottom and top both have a factor of 11. 55 over 11 is 5. And that is a beautiful answer. Boom! Number 2 is done. This test is great. We're doing awesome. Let's keep going. Let's see what happens on number 3. All right, so what do we got? Well, it says here we have a two-part problem. Notice here there's a part A and a part B. Now, almost always when you have a two-part problem, there is a connection between the two parts. So let's see what the two parts are. The first question, A, is the vector field conservative? We have to justify. Let's look ahead for B. What is B? Well, we have this curve C, terrible curve. Okay, but that's fine. It's a curve. Time goes from 0 to 1. And you want to find the following integral along the curve of that same vector field. Okay, now, here's probably the idea. If these problems are related, then somehow we want to use the fact of something about this being conservative or not conservative to answer this. But there's a cool fact that says, hey, if you're integrating a conservative function, your curve can be as ugly as you want. You only care about the endpoints. So, fingers crossed, part A, we're going to say it's conservative. Let's figure it out. So how do we tell? Well, if it's conservative, what would that mean? It would mean that this is equal to the gradient of some function f. Is that true? Is there some lowercase f function where if I take the gradient, out comes my vector field, and if I can find it, then I'm done. Okay, well, so let's think about it. If I took the derivative with respect to x, I'd have to get this, which means that, well, what would I have to have? I'd have to have e to the x squared, and I'd have to have xz. Because that's the only way, if I take the derivative with respect to x, I'd get 2x e to the x squared and xz. If I take the derivative with respect to y, well, I better get a y plus e to the y inside of f, because that's the way I get the derivative. And if I took the derivative with respect to, I took the integral with respect to z, or I took the derivative of f with respect to z, well, it says here it has to have an xz plus a z squared. Now you'll notice these match up, which is okay, no problem. In fact, we just string them all together, and we see that, aha, if I look at this function, f is e to the x squared plus xz plus y plus e to the y, plus z squared, then this is a potential function for my field. So conservative. And we're done. We've shown it's conservative because we found ourselves a potential function. And that's a nice thing. In fact, we're going to come back and use that. Now, are there other ways to show it's conservative? Yes, there are. We, for example, may have been able to take the cross product with the div, or if you like, taking the curl. And if we'd gotten 0, boom, conservative. But this is more straightforward, and it's useful because now we have not just the fact that it's conservative, we have the fact that it's a conservative, and we know the potential function. Because looking ahead, what are we going to do? Well, we want to take the integral on this crazy curve. Now, because we know it's conservative, what can we say? Well, because it's conservative, this is equal to the potential function, e to the x squared plus xz plus y plus e to the y plus z squared, evaluated at the endpoints. So there's a start, and there's a stop, or if you like, an end. Now, how do I find those? Well, the start is at time equals 0, and what do? I plug 0 into here. So if we plug in 0, what do we get? We'll get 0 minus 1, e to the 0, which is minus 1. I'm going to get 0 plus cosine of 0, log of 1. Log of 1 is 0, so that's going to be 0. Over here, I'm going to get 1 to the 1 minus 1, which is 0. So my start point is negative 1, 0, 0. Where's my end? Well, that's 1. And again, plug it in. So we plug in 1. 1 minus 1 is 0 times e. So 0. Then I'm going to get 1 plus cosine of pi halves times log of 2. But cosine of pi halves is 0, so we get 1. And here I'm going to get 2 to the 2, which is 4, minus 1, which is 3. 0, 1, 3. Okay, so almost done. Now we have to plug those in. All right, we plug those in. E to the 0 is 1. 0 times 3 is 0. Y is 1. E to the y is e. And z squared is 9. Subtract. Okay, plug in negative 1. E to the minus 1 squared is e. Negative 1 times 0 is 0. Y is 0. E to the 0 is 1. And 0 squared is 0. Now you'll notice here there's an e, which we can cancel. We can also even cancel a 1. And the zeros all are 0. We're left with a 1 and a 9, which gives us a final answer of 10, which is how many points we're going to get on this problem because we got it right. 10 points down. Yeah. All right. Good test. I am liking this test. Let's keep going. Number 4. So here we have an interesting problem. Let's see what it says. We have a line. In fact, we have 2 lines. Some line, blah, 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 and another line, blah, 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 are both tangent to the surface z equals f of xy at the point 325. Now, the word tangent means it touches. So it's just touching the surface. And we also know that f is differentiable at that point, which means that we can take derivatives. Another way to say that is that differentiable means it locally looks flat. Okay. And we want to find f sub x 3, 2 and f sub y of 3, 2. And there's a hint. And I'll say this test is full of hints. But how do you write the tangent plane? Notice here the tangent plane has been italicized, so it's like really emphasizing the word plane, plane, plane. Okay, let's key off of that. But anyways, tangent plane in terms of the partials. So let's think about what's going on here. So what do we have? We have some surface. It's hard for me to draw a surface, but we have a line. We have another line, and they intersect at the same point, 3, 2, 5. In fact, you can see they both have 3, 2, 5. And they both touch on the surface. Well, if you think about it, both those lines here are inside the tangent plane. So, what we can do is we can take our 2 lines that we've been given, and we can say, let's put those 2 lines together, and let's make our tangent plane. So what do we need to make the tangent plane? Well, we need a point. Easy. We know the point. The point is 3, 2, 5. So, what else do we need? Well, we need the normal. How are we going to get that? Well, for that, we say, look, we've got ourselves 2 lines. If I have the 2 lines, what I can do is I can take the directions of the two lines. Both those directions are in the plane, so we're going to take the cross product, and the cross product is going to be something perpendicular to the plane. So that's going to be the normal vector for the plane. So 3, 2, 1, you're going to cross that with 6, -2, -5. So again, 3, 2, -1, 6, -2, -5. Crossing those, that gives us our normal vector to our plane. Okay, so here we go. I, j, k. 3, 2, -1, 6, -2, -5. What do we have? Well, okay, so we start doing some math here. That's good. We've been doing that all semester. I times 2 times -5, -10i. J times -1 times 6, -6j. K times 3 times -2 is -6k. Lots of minuses here. 6 and 2 and k, that's 12k, but we went up, so that's subtract, -12k. -2 -1 times I, that's 2i, but we went up, so that's subtract 2i. And -5 times 3 times j, that's -15j, but we went in the other direction, so we add 15j. And we put it all together, and lo and behold, what do we get? We get -12, comma, 9, comma, -18. Cool. Now, we are paranoid because we want to get all the points. So, quick spot check. It's always good to spot check. You should do it. Recommend it, spot checking every few minutes if you can. So, what do we get? We're just going to quickly do a dot product. -36 plus 18 minus 18, 0. Good. Go ahead and do another one. -72. Ugh. Minus 18. Ugh. Okay, that's up to -90. Then the minus makes plus 90. 0. Good. So that is our right cross product. At least we got the direction good to go. And the direction is what we care about. Okay, so taking this cross product, notice here, -12, 9, 18, -18, they all have a factor of 3. So we can scale out, and let's just go ahead and divide out by 3. We get -4, comma 3, comma -6. Okay, so this will take as our normal. So we've now got our point to our plane, we've got our normal to our plane. Put those two things together, what's our plane? Well, we have -4x plus 3y minus 6z equal to something. Well, the something, that's where the point comes in. So it'd be -12 plus 6 minus 30. And if we put all those together, let's see, that's -42 plus 6 is -36. Now, that's the tangent plane. Of course, there's a hint here. How do you write the tangent plane in terms of partials? All right, so let's put this aside for a second. Let's think about this. Well, remember, our tangent plane would be z equals f sub x at our point, 3, 2, times x minus 3, plus f sub y, 3, 2, times y minus 2, plus f at 3, 2. So in other words, our tangent plane looks like this. You know, it's the value of the function at that point, and then you have the partials coming into play. Now, if you think about what that means, it really says z looks like f sub x at 3, 2 times x plus f sub y at 3, 2 times y plus some constant here. Now, I really don't care what that constant is, but the key here is that the coefficient for x and the coefficient for y are the f sub x and f sub y. Now notice I'm not saying that the coefficient for x here, -4, that's not saying that -4 is our answer, because we have to have it in a very specific form. So let's now solve our plane we had here for z. Sorry, solve for z. So if we did that, we'd get 6z is equal to -4x plus 3y plus 36, or z is equal to -4 over 6 would be -2/3 x, 3 over 6 would be 1/2 y, and 36 over 6 is 6. So this is the constant. I don't care about that. But now I say, aha, what's in front of the x? That's my f sub x. What's in front of the y is my f sub y. So we can conclude f sub x at 3, 2 is equal to -2/3, and f sub y at 3, 2 is equal to 1/2. And there's our answer. Nice. Now this is kind of an interesting problem because it's a little different than what we've seen before, but it's the same ideas. It's, in other words, let's take our tangent plane, let's figure out what it needs to be, and that's extracting information. So really this is more of a, do you understand what a tangent plane is? And hopefully the answer is yes, and we made it through this problem. Let's keep going ahead. Oh, yeah, I was hoping for one of these. These are some of my favorite types of problems. Change of variables. Cool. So what do we have? We've got this integral. It looks terrible. And, oh, hey, look, they even gave us the region. So we're integrating this very peculiar function over this kind of weird-shaped region here. And we want to carry out a change of variables. All right, well, let's figure out what happens here. So we've got a couple of things here. We know that u equals y plus x squared and v equals y minus x squared. So they gave to us the variables that we want to change. Okay. So let's figure out what we need to do. Now, this is one of those things. This is the one that involves the Jacobian. Now, how do we go through and do this? Well, there's a couple steps, okay. So let's just think ourselves through the process. The first step is you got to figure out the substitution, and here's the substitution that we're going to make. Okay, after you figure that out, then the next step is to go through and say, think about the pieces of the integrals. Remember, every integral has three pieces. There's the region you're integrating over, which you get from your bounds. There's the function you're integrating. And then there's the how do you break things up. So you have to go through and account for all those pieces. So here's what we're going to do. Let's think about what's happening here. Let's first do the how do you break things up. Because as the song says, breaking up is hard to do. So you should go ahead and get that out of the way first. Now here's how I like to do it, because there's two approaches. One is you could solve for x and y in terms of u and v. The other approach is, just focus on this and say, what is dx dy in terms of du dv? So if I want that, what I can do is I can do the following. I can say that the Jacobian xy, absolute value, times dy dx is equal to du dv. Or dv du, doesn't really matter. But the question is, what is this? What goes here? Well, for that, what we're going to do is we're going to take our partial derivatives. So we're going to take u sub x, u sub y, v sub x, v sub y. All right, so u sub x, that would be 2x, u sub y, 1. V sub x, that's negative 2x, v sub y, also 1. And take this 2 by 2 determinant, so 2x times 1 is 2x. Then I'm going to subtract negative 2x, giving us a grand total of 4x. So lo and behold, I can say the following. We can say that 4x dy dx is equal to du dv or dv du. Okay. Now you'll notice that x is always positive, so I don't need the absolute value. Okay, so this is going to be useful as we go on. All right, now the next thing is to say, okay, what's the function? Well, the function here, because I want to grab a 4x out, I'm going to really think of my function as being 2 e to the y plus x squared minus 4 y plus x squared. And remember, the 4x is going to come out dy dx. So that's going to be handled separately. So the function piece is that piece. Well, the 2e, and then I say, aha, y plus x squared, that's easy, that's u. So this becomes u squared minus 4u. And then this part here is going to become du dv or dv du. We'll decide that in just a second. And how do we decide that? Well, let's take a look at our region. We haven't done that yet, so let's think about it. Now, the way I like to do my regions is I think about each curve here. So, for example, y equals 8 minus x squared. Well, I want to rewrite that in terms of y plus x squared and y minus x squared. Now, I can do that by moving the x squared across. So y plus x squared equals 8. And I say, aha, that's u equals 8. Okay, how about y equals x squared? Well, that becomes y minus x squared equals 0, which is what? Well, y minus x squared is v. So v equals 0. Now, x equals 1 is a little bit more interesting. How do we do that? Well, it says that u is equal to y plus 1. And on the other hand, v is equal to y minus 1. So if I subtract, what do I get? Well, I get u minus v is equal to 2. All right. So in the plane, uv plane, what do we have? uv. Well, we have v equals 0, which is down here, v equals 0. We have u equals 8, which is over here, u equals 8. And then we have this curve, u minus v equals 2, or if you like, that's v equals u minus 2. So we intersect here at negative 2 and we go up. We cross here at positive 2, and there's our region. It's a triangle, and in fact, we should have expected it because the hint said it's going to be a triangle. Okay, cool. Now, we're almost there. So let's see, what does our integral become? Well, we've got to figure this out. So our integral 1 to 2, integral x squared, 8 minus x squared, 8x e to the y plus x squared squared minus 4y plus x squared dy dx is going to be equal to integral. A function is going to become 2e to the u squared minus 4u. And now I have to decide du dv or dv du. Well, looking at this, I can say, aha, that is a really messy, ugly function with respect to u. So let's do dv du, because I can definitely integrate with respect to v. Since I can't integrate with respect to u, and I can with respect to v, we're going to go order dv du. Okay, so that tells us a few things. It tells us what? Well, it tells us that we're going to have u on the outside. So u goes from where? 2 to 8. 2 up to 8. Then we have v. Where does v go from? Well, it goes from 0 up to this line. Now, this is the line. Remember, well, we wrote this, v is equal to u minus 2. So I'm going to go from 0 up to u minus 2. Now, as we said, easy integral. So this becomes integral 2 to 8 of 2v e to the u squared minus 4u du. And we're going to evaluate v from 0 to u minus 2. And now if we plug that in, what do we get? Well, we're going to get that this is the integral 2 to 8. And here, 2 times v is going to be 2u minus 4. And it's e to the u squared minus 4u du. And it looks like, terrible integral, but check it out. It's almost as if they planned for this to happen, because they did. If I take the derivative of u squared minus 4u, that's 2u minus 4. So this is simply e to the u squared minus 4u from 2 to 8. So we plug this in. So that becomes e 64 minus 32 is 32. Then I have 2, and that's 4 minus 8. That's e to the minus 4. E to the 32 minus e to the minus 4. Beautiful answer. Nice problem. Really interesting. This one is I like this kind of problem because it's sort of, you have to do a little bit of changing variables, pay attention. You have to think at some point, okay, what's the right order of integration? But if you're careful, the problem has a way of working itself out. This is nice. We're making great progress. This is a pretty good test so far. I'm liking where it's going. Let's see what number 6 gives us. And, okay, it's an absolute max and absolute min. Now, these are not hard problems conceptually, but they're a little bit tedious, but that's okay. You know, it's a trade-off. Let's go ahead. Let's see what we have. We've got a function, 2x squared minus 4xy plus 4y squared minus 2x. And we have this triangular region. And in fact, they were nice enough to draw here. There's the 0, 0. There's the 2, 2. There's the 2, negative 2. And it says, note the parameterizations of the sides are t comma t. Well, that's this side right here. This is the side of t comma t. And then there's t comma negative t. That's this side over here. So t comma negative t. And then there's 2 comma t. Well, that's x is constant 2. So 2 comma t is this side over here. And it says there are 6 boundary points and 1 interior point to be checked. So we got to come up with a list. We better have 7 points on our list or we're in trouble. Okay, let's start with the interior point. So for the interior point, we need to say, when does the gradient equal 0? Well, really that says, when does f sub x, which is what? Well, that's 4x minus 4y minus 2 equals 0. And f sub y, which is what? Well, that's minus 4x plus 8y equals 0. Now, from this bottom equation here, what can we do? Well, we can do a lot of stuff. Actually, maybe let's do this. If we just add these two equations together, the x's cancel. Minus 4y plus 8y becomes 4y minus 2 equals 0. And so from here we get that y equals 2/4 or y equals 1/2. And once I know y equals 1/2, I can put it into here. And this would say that minus 4x plus 4 equals 0 or x equals 1. And therefore, on our list, we have to have a list somewhere. Well, let's be optimistic. We'll make our list down here. We're going to have the point 1, 1/2. Because again, x equals 1, y equals 1/2. All right, 1 point down. Now, next, let's just throw in the corners. Those are always freebies. So we have 3 corners. Corners here, 0, 0, 2, 2, 2, minus 2. Okay, so add those to our list. 0, 0, 2, 2, and 2, minus 2. So corners. Okay, what's next? Well, we have the 3 sides. Let's just do them systematically. So t, t. So for the side t comma t, what do we get? Well, we rewrite our function as a function of a single variable, g of t. So I put it in, that's f of t comma t, which is 2t squared minus 4t squared plus 4t squared minus 2t, which simplifies nicely. That's 2t squared minus 2t. And take the derivative, g prime of t would be 4t minus 2. Set that equal to 0, and we get that t equals 1/2. And because we are at t comma t, that gives us the point 1/2, 1/2. So if we were updating, so we had the corners, we had the interior point, and now we have this point here. So adding it to our list, 1/2, 1/2. Okay, what's next? Well, let's do the other diagonal, t comma negative t. So we have g of t would be f t comma negative t. Well, what changes? Not too much. So we're still going to have 2t squared, but now instead of minus 4t squared, we have a plus 4t squared plus 4t squared minus 2t, which becomes 10t squared minus 2t. Take the derivative, g prime of t, that's 20t minus 2, so that equals to 0. And if we do that, we get t equals 1/10, which is a small number, but 1/10, negative 1/10. So really close here, almost right next door. So 1/10, negative 1/10. Okay, last side. That's the side 2 comma t. So again, we're going to get to a function of single variable, f of 2 comma t. So everywhere we see an x, we put a 2. Everywhere we see a y, we put t. So we're going to have 2 times 2 squared, that's 8, minus 4 times 2 times t, so that's minus 8t, plus 4 times t squared, 4t squared, minus 2 times 2, so that's minus 4. So there we go. Really not much to simplify here. 4t squared minus 8t plus 4. So we take the derivative, and we get g prime of t was what? Well, that'll be 8t minus 8. So that equals to 0. And we get t equals 1, which gives us the point 2 comma 1. And that's our 7th point. Yes, let's check. 1, 2, 3, 4, 5, 6, 7. Okay. At least we got 7 points. That's a really good sign. Okay, so what's next? Well, we got to plug in and evaluate all these points. And I'll tell you, it's times like these when you're like, man, I really wish we had the calculators back. But that's okay. We just got to be patient. As long as we're patient, we can work our way through the problem. So because we're having a hard time putting this all on the screen, for reference here, we'll just recall that our function f of xy is equal to 2x squared minus 4xy plus 4y squared minus 2x. Okay, so we're going to evaluate each one of these points at f, 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 f. Okay, and see what we get. Now, some of these are more fun than others. In fact, let's just go ahead and get the fun one out of the way. 0, 0, 0, 0, 0, 0. 0, minus 0, plus 0, minus 0, equals 0. Okay, okay, fun one is done. All right, 1 comma 1/2, so that would be 2 minus 2 plus 1 minus 2, which is equal to -1. Good. All right, 2 comma 2. So that's going to give us 8 minus 16 plus 16 minus 4, which is 4. 2, -2. Very similar. 8. The only difference here is this middle one is not subtracting 16. Now we add 16, and then still plus 16, and still minus 4. And that will give us a grand total of 36. Because 16 plus 16 is 32, plus 8 makes 40, subtract 4 is 36. 1/2, 1/2. Well, 2 times 1/2 squared, that's 2 times 1/4, that's 1/2. 4 times 1/2 times 1/2 is -1. 4 times 1/2 times 1/2 is 1. Minus 2 times 1/2 is -1. And so I get 1/2 minus 1, -1/2. All right? 1/10, -1/10. Okay, this one we've got to be careful on. 2 times a 10th times a 10th. That's 2 over 100. Then I'm going to get -4 times a 10th times a 10th. So that's -4 over 100. Wait, sorry, whoops, I forgot the minus sign. So that's plus, because remember, one of these is positive, one of these is negative. Then plus 4 times the 10th times the 10th is again 4 over 100. And then I have minus 2 times the 10th. So that's 2/10, but I'm going to update it, so put it over 100, so that's minus 20 over 100. And if we do this, 2 plus 4, that's 10. Minus 20 is -10, -10 over 100, also known as -1/10. Finally, 2 comma 1. What will that be? Well, that's going to be 8 minus 8, then plus 4, and minus 4. And we put that all together, we get 0. Okay, so we're almost done. We've done all the hard parts. The easy part, that's all that's left. We have to go through our list and say, which is the smallest number? And the answer is the -1. So this is our absolute min. Now notice we wanted the value, not the location. So -1 is the absolute min. It's not 1 comma 1/2. That's where it happened. It's the -1. What's the largest number? And the answer is 36. And therefore, this is our absolute max. Good. All right, and now we're done. -1 and 36. Okay, so we're making great progress. Aha! Last one, number 7. This was only a 7-problem test. Okay, here we go. Let D be the solid. X, Y, Z greater than or equal to 0, Y less than or equal to 1, X plus Z less than or equal to 1, Z less than or equal to 1 minus Y squared. Oh, good. They gave us a picture. I love it when they give me a picture. This top part looks a little bit pointy, but that's okay. And let S be the surface of D. Find the following. Now, D of SA equals D sigma. This is just different notation for doing surface integral. So we're integrating on a surface, some horrendously looking vector field, dot n, D sigma. Well, okay, so first off, I got to say, this is an interesting test since we're going through it. Notice, there's a typo here. They actually did D in 2 different ways. Now, some people might complain and say, whoa, this is flawed. They got to throw all these test results out. But I like to say it gives the test character. We've had mistakes on the test in the past. There's, of course, who can't forget the fall 2011 test? Oh, man, that was crazy. But anyways, those both mean the same thing. Now, what do we have here? Well, we're integrating something. This is essentially the integral of f dot n d sigma. Okay, on a solid, well, that says what? We better be using the divergence theorem. Okay, divergence theorem. So this is going to be the integral over the whole solid d of div f dv. Okay, so before we worry about how to set this up, what does this become? Well, this is the integral over the whole solid of the divergence. So I come here, take the derivative of the first term with respect to x, the secant squared z is gone. It's just simply 20. Take rid of the second term with respect to y. This part with the log 1 plus z goes away, and that's going to be 10 cosine squared x. Go to the last term, take the derivative with respect to z, and here that part drops out, and I'm going to get 10 sine squared x, because 10 z sine squared x dv. Now, cosine squared plus sine squared, awesomest trig identity. You should know if you're going to get a tattoo of a trig identity, that's the one you should have. Of course, we already know we've got it tattooed all over our hearts, so we don't need to do it anymore. Okay, the 10 comes out. Cosine squared plus sine squared is 1. 20 plus 10 is 30. So really, we are integrating over our solid of 30. Good. So now we have what we want to do. We're basically just sort of saying 30 times the volume is what we're after. Okay, so now we actually have to set up this integral, but notice we have a hint. Hint, dx, dz, dy. Well, that's suggesting a couple things. One, it's suggesting that we use rectangular coordinates, and given that we don't have our rotational symmetry here, if we had rotational symmetry, we would use our cylindrical coordinates. We don't have that, and we definitely don't have spheres or cones, so we don't want to go spherical. So yeah, okay, we're going to go with our Cartesian coordinates, and let's just go ahead and follow the suggestion, dx, dz, dy. Okay, so this will be integral, 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 30 dx, dz, dy. So we've got to figure out our bounds. So since x is the last set of bounds, I'm going to look down the x-axis, and if I do that, I see here in the yz plane, I see my curve. What curve do I see? Well, I see this curve here. What is it? Well, if I look at it, this is the curve z equals 1 minus y quantity squared. All right. And here is at 1, here's at 1, and there I go. So where does y go from? Well, y goes from 0 to 1. So 0 to 1. Where does z go from? Well, it goes from the bottom part here, z equals 0, up to this top part, z equals 1 minus y squared. 0, 1 minus y squared. And finally, how about x? Well, x is going to go from the back face here forward until I hit this front face. Now this back face, that's the plane, that's the yz plane, that's x equals 0. The front face is what? Well, that's the plane x plus z equals 1. So that's going to be this plane x plus z equals 1. Now I want to solve for x, so this is going to go up to 1 minus z. And there we go. Okay, so we're almost done. We've got our integral set up. We just got to go ahead and evaluate. So let's go ahead. Let's see what our answer is. 0 to 1. 0, 1 minus y squared. Easy thing to evaluate. So this is going to be 30x. Going to go from 0 to 1 minus z. Dz, dy. And so this is going to be integral 0 to 1, integral 0 to 1 minus y squared of 30 minus 30z dz, dy, because I can just plug in 1 minus z. 30 times 1 minus z is 30 minus 30z. Okay, so we evaluate that. That's going to be integral 0 to 1. Integral of 30 is 30z. And I'm going to have minus 15z squared. And I'm going to evaluate z equals 0 to z equals 1 minus y squared. Okay, so what do we have there? dy. What do we get? Well, this is equal to the integral 0 to 1 of 30 times 1 minus y quantity squared minus 15 times 1 minus y squared squared, or 1 minus y to the 4th dy. Now, at this stage, we could be like, well, I could expand everything out and hope I expand correctly, or we can be smart. And, well, we're in calculus. Calc 3, we should be smart now. Let's do a substitution. Let u equal 1 minus y. Then du would be negative dy. Okay, and what would we get? Well, this would become equal to, if we work it out, our bounds would become 1 to 0. And then our du is minus 2i, so we're going to put a minus out here. Then we have 30u squared minus 15u to the fourth du. So if we just swap the bounds, gets rid of our negative sign, so this becomes integral 0 to 1 of 30u squared minus 15u to the fourth du, and we evaluate. Integral of this would be 10u cubed, because I'm going to divide 30 by 3, minus 3u to the fifth, because I'm going to divide 15 by 5, and I'm going to go from 0 to 1, which is going to become, plug in 1, I get 10 minus 3, subtract 0 minus 0, giving us a final answer of 7. Oh my gosh, they did it. Those crazy guys. The problem number 7, answer was 7. I've seen this before. This is one of the fun things they like to do. It's one of those things that make you say, oh yeah, must have gotten it right. No way we'd get such a beautiful answer by coincidence. And that's it. That's the whole test. Because remember, the last page was blank. It was scratch paper. So there we go. That was the whole test. I gotta say, nice test overall. A little bit too computational for number 6 for my taste. Some good pictures. A nice mix of results. I have to say, overall, I would probably rate this test maybe 4 out of 5. A good test. Could be better. Could have had more problems on it. But the problems that there were good variety. Let's just put this test back together. Okay, and there we go. And there we have it. The Fall 2017 Math 265 final exam. And we'll put it back in where it came from. And don't forget, if you're ever going to turn a test in, you always want to get credit. So we put our name, Kapla, which of course we all know means success in Klingon. So thank you for joining me, and we'll see you again when we unbox our next test. Have a good day.